All right, perfect. So my name is Andrew, and my co-author is Ivan Rivera from California State Polytechnic University. And today we're presenting a cost-effective approach for continuous freshwater monitoring using machine learning. So a quick overview of the agenda. We have an introduction with the significance of nutrient monitoring, and then we have a methodology and results and conclusions at the end. So for some background, um, the two major components of fertilizer, which is overwhelmingly being used in global agriculture, is nitrogen and phosphorus. And so as we expand agricultural production for a growing population, we're going to have more and more of these components that will eventually run off into water bodies. So in this study, we're looking at freshwater bodies where phosphorus is limiting nutrient. So essentially that means that when phosphorus enrichment occurs, there is significant growth in algae and cyanobacteria, which can cause eutrophication. So essentially the eutrophication process, you can see here with this very eutrophic waterway that the cyanobacteria take up all the excess nutrients that have been washed from primarily agricultural land, and they will bloom, which means that like their population grows rapidly. And once this nutrients has all been used up, they will die off. And so that way, you suddenly have an influx of organic matter that is decomposed aerobically, and all the dissolved oxygen in the water is used up, which can cause hypoxia and lead to dead zones where fish and other marine organisms are suddenly killed. And this process causes an estimated $2.2 billion in annual economic loss in the US alone by some estimates. So in order to manage eutrophication, we have to be able to monitor and manage nutrient runoff. So this is traditionally done with grab sampling, where a researcher or technician goes out into the field and takes a sample 12 to 18 times a year and then brings it to a lab to be processed. So that this low frequency and slow processing time causes potential for like patterns to be missed in between different sampling sessions, and also delays the ability of management decisions because it takes a significant amount of time to process these samples. Then we have wet chemical sensors, which are automated systems that are quite costly at $10,000 or more per unit. And they also produce a continuous chemical waste that has to be handled and disposed of. Optical UV sensors, which work for both nitrogen and phosphorus, are also significantly costly at $15,000 to $25,000 per unit. And for nitrogen, which is not the limiting nutrient in freshwater situations, there has recently been a development of ion selective electrodes, which are low cost at around a few hundred to $1,000, but they have measurements that drift over time, so there needs to be constant maintenance and calibration. So the goal for this research is to use machine learning techniques to supplement these existing high-cost options. So essentially, the approach here, we have to take existing data from testing sites across the United States, filter them, identify surrogate indicators, and then we train machine learning models with those surrogate indicators. And the main reason for this process is because there are many like individual testing samples, but the amount that actually line up and are usable for machine learning purposes is very minimal, as we'll see in a moment. So first off, we can cover the source of the data. It's coming from the Environmental Protection Agency water quality portal. So it covers testing data from sites across the US. And for this study, we're looking at freshwater, which means this selection of lake, reservoir, and impoundment, which are freshwater bodies. And the data range is from dates between July 5th, 2022 to 2023. Then we use the EPA's tools for automated data analysis to remove nonsensical values that may add noise to our machine learning processes. So this includes invalid units, non-numerical units, and duplicate values that are in the data set. And that ultimately removes 85,000 of the 700-ish thousand tests that were present in the whole data set. Then we have pre-processing. So this is primarily used to address the format that the data was in. So the raw data is available in the database of the EPA separately with each characteristic, say dissolved oxygen or phosphorus concentration, separate from all others that even if they were measured at the same time. So first we identified discrete samples based on ones that were taken at the same longitude, latitude, and time. So effectively, we made the assumption that if two tests were performed on samples that were from the same location and time, that they are corresponding to the same water. And then we had to convert to consistent units within each characteristic because many of the different testing sites use different units. And in this process, we found that using micrograms per liter is better than using milligrams per liter because it leads to greater differentiability and variance between the values that the machine learning models will use. So one of the main challenges for water quality testing in general and this project specifically was that data is missing not at random. So essentially we had a lot of characteristics, 713 of them, and no single testing site tested for all of them at once. So since testing sites typically decide what indicators they test on based on like local policies, the missing values can't be explained by the ones that are present in the data set. So to circumvent this issue, we identified surrogate indicators using permutation importance. So first we trained two models, histogram gradient boosting regressor and random forest, on the full data set with all 69,000 discrete values and 713 characteristics. So histogram gradient boosting regressor was selected for its native support for missing values and also its relative efficiency due to its binning process. So effectively, it can process large data sets by grouping or data sets with many features by grouping values within each feature together. And permutation importance was selected because it avoids the potential of feature importance, which is one of the features of random forest, to identify non-predictive features when the model is overfit, which, as we'll see later, was the case for both of these. So with histogram gradient boosting regressor, these were the 5 features found most significant in phosphorus concentration prediction. And then ultimately, these chlorophyll A and pheophytin A were eliminated due to the lack of testing of these two with all of the other ones. So if they were included, we would only have 126 samples or 8 samples compared to the 2014 that sample size that without them. So after these surrogate indicators were identified, we fit the rest of the models to this new smaller filtered data set because many of these models are unable to handle missing values natively. And for our benchmark, we use linear regression for its simplicity and wide application in both water quality regression and regression prediction tasks in general. And that resulted in an R-squared value of 0.425 and 0.441 for training and test sets, respectively. The train test split that we found most effective was 0.6 train to 0.4 test. So that's the split that is used for all of these models. Then we have random forest, which was the best performing based on this data set with a test R-squared of 0.565. Oh, sorry. Gradient boosting regressor actually slightly outperformed that with 0.593. And histogram gradient boosting regressor approaches gradient boosting regressor and shows potential as a more efficient model for larger data sets. Meanwhile, KNN only marginally outperforms the linear regression benchmark, and both support vector machine and decision tree are unable to match the benchmark. Decision tree is hilariously overfit with 0.999 training R-squared and a negative 0.01. Since these ensemble tree methods are essentially building on decision tree, we chose not to continue refining decision tree, although this could be brought down significantly. Then we chose to optimize hyperparameters. So those R-squared values were using the default hyperparameters from scikit, which is the utility that we use to test these models. But we sought to increase the R-squared value to see how effective it could be. So we chose to use Bayesian optimization because it is a significantly more efficient model, which in the real world has cost implications. So the typical two optimization models are grid search and random search, which do not recursively improve on themselves. And so whether or not the objective function is actually being maximized, they'll always take the same amount of time. Meanwhile, Bayesian optimization recursively expands on itself, so it approaches the optimal values faster. And in our findings for the final hyperparameters, we noticed that all of the changes were primarily targeted overfitting in the trained data set. So with histogram gradient boosting regressor, the max spins and iterations were reduced. So that way, effectively more of the data within each feature was blurred, and there were less opportunities to pick up on random variation and noise in the training set because there are less iterations. And with random forest, a max depth was set, which limited the nodes in each of the estimators and similarly prevented too much noise from being picked up. So here you can see a chart that shows the R-squared values that were depicted in the graph, with random forest showing the greatest amount of improvement at around 14%. Before a conclusion, we found that for the purposes of water quality testing and nutrient monitoring within freshwater systems, ensemble trees showed the most promise for nutrient monitoring. So we also applied the same methodology to nitrogen methods or nitrogen concentrations, and achieved a slightly higher R-squared value across the board. For future research, we should consider working with a larger data set. Even though we started with over 700,000 testing values, the data set ultimately was whittled down to 2,000. So perhaps with a longer testing, longer time frame of testing, we would be able to better evaluate these models in more similar to real world conditions. It's also worth testing imputation methods. Although the basic exploration we did on this data set did not show significant improvement because due to the large number of missing values, perhaps a more advanced imputation method is better able to improve accuracy. And finally, one more direction that this could go is an Internet of Things approach, where a sensor package is actually built using off-the-shelf parts that could test for these surrogate indicators, and then a machine learning model is fit to data from that so that we actually have a deployable solution. And that is all for today. Thank you for your time.